As we continue working with radicals, we're going to talk about dividing radicals, or the division property of radicals. And in doing so, we want to be able to perform division of radical expressions and rationalize the denominator when necessary. And just to look at rationalizing the denominator, going back to things that we have previously known, denominator, if we're talking about a denominator, we are talking about a fraction. And we always have a numerator over a denominator, and in the past we may have a number over a number, and that is 3 over 4, or 3/4. What we quickly learned about fractions is we weren't allowed to have decimals per se in the denominator, and that would actually have become 30 over 45. So we don't want to have parts in the denominator because that is representing the whole of something. And for example, we also eliminated, you may not see 2 over 3/4. We don't want a fraction within a fraction, and the same thing goes when we have a radical. We don't want to see the square root of 3 in the denominator because that is a decimal. If we were to put that in the calculator, it's a decimal. It doesn't work out to a whole number. So that's why we need to rationalize the denominator to get this radical out of the denominator, just like we would have gotten a decimal out or a fraction out of the denominator. And then that's just as a understanding why we do that. And then the conjugate, we'll use the conjugate to help rationalize the denominator. And we most recently used the conjugate when we talked about complex numbers and eliminating those complex numbers in the denominator. And a conjugate is when we have x plus 1, and the conjugate of x plus 1 would be x minus 1. It's the same binomial. The only thing that changed is my operator. So that is leaning forward into what we're going to talk about, that what we want to be able to do is how can you write a ratio of a radical expression in simplest forms. So as we talk about the quotient property of radicals, we would look at the a to the nth root over b to the nth root is the same thing as a over b to the nth root. So that's the property that we can just create that fraction underneath the radical. And of course, one thing we want to identify is that b cannot equal 0, and b cannot equal 0 because then we would have an undefined number. Often you'll see these limitations in there which just creates something undefined, so often ignored, but just understanding that b can't be 0. So as we look at some examples, as we look at this, we want to be able to find out what is our simplest form. And I have the square root of 25x squared y squared over the square root of xy. And I could go ahead and find this square root because 25 is a square root, x squared is a square root, and y squared is a square root. However, I'm going to be left with a radical in the denominator, and we can't have that. So let's go ahead and just use the quotient property. I'm going to use the quotient property to rewrite this fraction as 25x squared y squared over xy. And now I can go ahead and simplify what is in my radical. Okay, so I know that looking at that, 25 over 1 is just going to remain 25. And then I know that x squared divided by x is going to be x to the first. X to the first using my exponent rules. And then the same thing with, goodness, how about if I just say that it's going to be x to the second minus 1 times y to the second minus 1, right? Because those are exponents of 1. All of that over 1. So then we end up with the square root of 25xy. So when we simplify that, again, that is going to simplify as, or rewrite it as, the square root of 25 over the square root of xy. And I know that the square root of 25 is 5, so we end up simplifying that down to 5 square root of xy. And I showed you a lot of steps there. It was potentially easier than I showed it to you, but I need to make sure that you see all the thinking that's going along, and we just don't go from one step to the other without doing a good explanation. In our next example here, we're looking for to simplify the cubed root of 8110 x to the 10th power over the cubed root of 3x. And using the quotient property again, we have the cubed root of 81x to the 10th over 3x, which is going to be 81 divided by 3 times, x to the 10th minus 1, right, because that's doing my exponent properties. So I know then that the cubed root, let's see here, of 81 divided by 3 should be 27, and then that will be x to the 9th. And the cubed root, remember the cubed root, I'm looking for things that I multiply times itself 3 times. So it turns out that 27 is a perfect cube, and if I need to write that out, right, 3 times 3 times 3 is going to be 27. And x to the 9th is actually going to be a cube root, because that would be the same thing as x to the 3rd times x to the 3rd times x to the 3rd. So when finding that cube root, I'm able to say, okay, well, the cube root of 27 is going to be 3, and the cube root, that was 3, and the cube root of x to the 9th is going to be x to the 3rd. So there you go. There's my simplified root. And, you know, it's just a matter of working with it and getting practice and using the properties as we move along. So as we work with rationalizing the denominator, what I want to do is I want to rewrite the expression with no radicals in the denominator. And if we look at an example, if we have the square root of 1/5. All right, now that would be the same thing as the square root of 1 over the square root of 5. Well, what I want to do is I actually want to create a perfect square in the denominator that will allow me to get rid of the radical. And so what I can do in order to create a perfect square in the denominator, if I have the square root of 5, what would make that a perfect square? Well, if I multiplied that by another square root of 5, I would have the square root of 25, or just 5. But I can't just multiply the denominator. I have to multiply the numerator also, because I'm multiplying by the value of 1. The square root of 5 over the square root of 5 is 1. So I haven't changed its overall value of the expression. So this then becomes, as I multiply across, the square root of 1 times the square root of 5 is going to be the square root of 5. And then the square root of 5 times the square root of 5 is going to be the square root of 25. And then when we simplify, I would have the square root of 5 over 5. So I was able to rationalize that denominator by removing the radical from the denominator, and there you go. That would be that in simplest form. Now, this is a little bit more of a challenging example, but what I'm trying to do again is rationalize the denominator. And I am looking for, in this problem, I have a cube root, so I have the cube root of 3 over the cube root of 2x. So in order to rationalize this radical, I'm going to need to find a perfect cube because I'm looking for the cube root. So I know I need to use 2 as a perfect cube, and I need to use x as a perfect cube. And just think about it. 2 times 2 times 2 is going to be my perfect cube, which is going to be 8. So if I were to multiply 2 times 4, that would give me 8. So that would create my perfect cube. So if I go ahead and do some thinking here over the cube root of 2x, then I'm going to multiply it by the cubed root of, well, we just said 4, and then x. Okay, well, x times x times x is a perfect cube, and that would be x to the 3rd. Well, I need to multiply x times x squared in order to get a perfect cube. And then there we go. There I was able to find the information I needed to rationalize this denominator. So I'm going to multiply this expression by the cube root of 4x squared over the cube root of 4x squared. And now I'm going to go ahead and multiply it out. So let's see where we're at. We have the cube root of 4 times 3 is going to be 12x squared over the cubed root of 2 times 4 is 8, which is what we're looking for, a perfect cube, and then x to the first times x to the second, which is going to give me x to the third. So now I can actually find the cube root of that denominator, and that is going to be 2x. 2x over the cubed root of 12x squared, because there's not a perfect cube in 12 or in x squared. And let's see if I need to show this right here. The cubed root, 8x cubed, is going to be the same thing as 2x times 2x times 2x. So that's how we came up with that denominator. So there you go. There's another example of being able to rationalize the denominator with something other than a square, but a cube. And we'll move on to working with the conjugate in rationalizing our denominator. Okay, so as we are using a conjugate to rationalize our denominator, and if you wonder why, well, before we just had a monomial or one term in the denominator, but here we have this operator involved, so we have radicals separated by addition or subtraction, so we need to use a conjugate to be able to eliminate that. And in doing so, what we want to do is step one is we want to multiply the numerator and denominator by the conjugate. So looking here, my conjugate is going to be just the opposite sign. So I'm going to have 2 square root of 2 over the square root of 3 minus the square root of 2 times. The conjugate of the denominator is going to be the square root of 3 plus the square root of 2. And again, I need to multiply both the numerator and denominator by that. And in doing so, I'm going to go ahead and multiply this out. So remember, let's see here, we'll just write this here, that I have 2 square root of 3, 2 square root of 2, there we go, 2 square root of 2 times the square root of 3 plus the square root of 2 over the square root of 3 minus the square root of 2 times the square root of 3 plus the square root of 2. Now, and I wrote it this way just so you can see that we're using the distributive property, right? I'm going to multiply that times both terms, and then in this I have 1, 2, 3, 4 terms, so I'm going to end up using the FOIL method. So, or whatever method you like to multiply binomials by. So that is going to equal, that numerator is going to be 2 square root of 2 times the square root of 3 plus 2 square root of 2 times the square root of 2 over the square root of 3 times the square root of 3 plus the square root of 3 times the square root of 2, then minus the square root of 2 times the square root of 3 minus the square root of 2 times the square root of 2. So again, square root of 2 times square root of 3 right here, square root of 2 square root of 2 times the square root of 2 right here, square root of 3 times the square root of 3, the square root of 3 times square root of 2, the square root of negative 2 times the square root of 3, and the square root of minus the square root of 2 times the square root of 2 right here. So as we simplify this, this is going to become 2 times the square root of 6 plus this is going to become 2 times the square root of 4 over this is going to become the square root of 9 plus this is going to be the square root of 6. This is going to be minus the square root of 6, and then this is going to be minus the square root of 4. So things that we can look at, well, I have a positive and a negative square root of 6, so those two things are going to cancel out. There's not going to be a lot I can do with this expression because square root of 6 doesn't have a perfect square in it, but I will be able to change this expression. The square root of 2 is 2, so this is going to be 2 times 2, or 4. This is going to be 3, and this is going to be minus 2. So we end up with 2 square root of 6 plus 4 over 3 minus 2, which is 1. So the answer is going to be 2 square root of 6 plus 4. There you go. We were able to simplify that radical by using the conjugate. So as we close out dividing radicals, we wanted to be able to perform division of radical expressions and rationalize the denominator when necessary. So remember, rationalizing the denominator is removing the radical from the denominator, and we did that by creating that perfect square or also using the conjugate. So you can simplify a ratio of radical expressions by applying the quotient property of radicals and rationalizing the denominator. And the quotient property, again, is going to be something along this, right? If I have the nth root of a over the nth root of b is the same thing as the nth root of a over b. And then conversely, the nth root of a over b is the same thing as the nth root of a over the nth root of b.